I would like to welcome you to this wonderful tutorial on chip memories, challenges, opportunities, and recent advances, in which the speakers, tutors are Professor Manan Suri of IIT-Delhi and Professor Anuj of IIT-Delhi. I've had the privilege of knowing these two gentlemen for a long time, and it's my pleasure and privilege to know them and to learn this difficult subject from them. Dr. Anuj Grover is Associate Dean of Industrial Relations and Associate Professor in the Department of Electronics and Communication Engineering at the IIT-Delhi in the Indraprastha Institute of Information Technology. He also is a great innovator and chairs the Institute Innovation Council. He will introduce himself during his presentation at the opportune moment. My esteemed colleague in IIT-Delhi, Dr. Manan Suri, he's the leader of the Non Volatile Memories and Neuromorphic Hardware Research Group at IIT-Delhi. His research interests include semiconductor non-volatile memory technology and its advanced applications in neuromorphic, artificial intelligence, security computing, and sensing. Again, he's a globally recognized figure and a deep tech innovator. He will introduce himself to greater depth during his talk. So without wasting further time, I would like to hand over to Dr. Anuj Grover. Dr. Grover, will you please take over?
Good afternoon, everyone. So thank you, Professor Kaushik, for introducing me and for your kind words. We will move to the presentation right away. So as you already know, the title of our presentation on this tutorial today is On Chip Memories, Challenges, Opportunities, and Recent Advances. This tutorial is being jointly conducted by me and Professor Manan Suri from IIT-Delhi. The way we plan the tutorial is that I will take the first part of the tutorial where we will talk about embedded SRAM design, challenges, and opportunities. This session will be about 35 to 40 minutes. While I would encourage you to ask questions if you have any during the session also. We will also have a dedicated Q&A time after the session. Then Dr. Manan will take over and he will talk about NVM design challenges and opportunities. And likewise, there is a 35 to 40 minutes window in which he will talk, and then there will be a 5 to 10 minutes window of question and answers. So let's start with part one. And let me begin with introducing myself. My name is Dr. Anuj, and I've been working in VLSI design for more than 21 years now, of which more than 18 years has been with ST Microelectronics. I have multiple patents and papers in my name, and my primary area of research is circuits and systems, memory design. These days, I am focusing heavily on in-memory compute, and we'll talk about it later. And I also work on safety and security in hardware. Amongst my other interests, I'm interested in innovation, leadership, well-being, self-growth, and I'm also a TRIZ Level 3 certified practitioner. So TRIZ is a technique for inventive problem solving, and I really enjoy using TRIZ. If you wish to reach out to me, my webpage, email address, and YouTube link are there on the site as of now. Before we go further, let us answer this question for ourselves. Or in fact, let me just introduce IIT-Delhi also to you. It's a state university established by the government of Delhi in 2008 and has been ranked well by different ranking agencies over the past few years. It has 7 BTech programs and 8 MTech programs with specializations in VLSI and embedded systems as one of the ones in MTech programs. We have PhD programs across 6 departments, and if there are students who are interested in pursuing PhD, I can assure you IIT-Delhi is a good place to be in. Before we start, let us look at why this tutorial in the first place. Why are we even talking about embedded memories and the challenges or the opportunities that exist there. Many of you may have seen that across the hierarchy of the compute systems that we use, processors, there is a wide range of memories that exist. There are on-chip registers, which are right there in the data path. And then there are level 1 caches, level 2 caches, and so on. Until we go to off-chip, main memory, DRAMs, and off-chip non-volatile disks. In recent times, non-volatile memories have also gone on-chip, and that is where Manan's research area, and that is where we will also talk about on-chip non-volatile memories also today. And when we say that memories are all over the place, it's not just a statement per se. A quick look at one of the recent chips, let us say AMD chip called Ryzen, would indicate to you that there is a vast area of the chip that is being occupied by the memories. In fact, you will see that up to 70% of chip area in advanced digital SoCs is consumed by memories. Let me just take a moment to share that slide with you. Just give me a second. So SRAMs, in those terms, on-chip SRAMs are a major part of any digital SoC, and this in itself is a reason enough for us to look into this tutorial with sufficient interest. For example, all this pink region in the center, in fact, all this region is L3 caches. Over here, you have L2 cache regions, and all this is L1 cache. This is L1 cache. So if you just look at it, this is a huge chip real estate that memories occupy. A small error anywhere can mean that the entire chip is simply thrown away. That is the importance of SRAMs, and that is the importance of on-chip memories in today's designs. So what are we going to look at today? In the beginning, we will look at SRAM design, the architecture, 60-cell operation, and verification challenges and opportunities. And then, as I mentioned, one of my recent and key interests is in memory compute. We'll also look at some details of what in-memory compute means, what does von Neumann bottleneck mean, then the key design choices, and recent results and recent experiments and results from across the world will also be summarized towards the end. So typically, any memory is organized like this. There is an array of storage elements, and then there are peripheral circuits, decoders, IOs, multiplexers, which would enable any user to access this array of storage elements. The memory operation essentially involves, input clock and some addressing scheme. When the clock arrives, internal clocks are generated, addresses are pre-decoded, and they go into what is called as post-decoders, the decoder region. Once the clock reaches the post-decoder region, we generate what is called as a word line. The word line selects memory cells, and I'm showing a differential memory cell over here. When the memory cell is selected, the bit lines, so these are the pairs of bit lines in there, they discharge. A differential voltage appears between the bit lines, and then we have what is called as a sense amplifier that is activated, and the output is made available to the user. This is the typical read operation in a SRAM. Now, we may have many more additional features. We could have test features, we could have security or debuggability features also added in, but this is the core read operation in an SRAM, which is enabled by what is called as a 60 memory cells. In fact, SRAMs could have different kinds of memory cells, but 6 transistor memory cell is the most common one. A 6 transistor memory cell is essentially a latch which has pull up PMOSes and pull down NMOSes, and then a pair of excess transistors through which the information inside the memory cell is transmitted onto the bit lines. Let us have a quick look at how the memory cell operates. Initially, the bit lines are pre-charged to a particular level. Let us say, assume it to be VDD for now. When the word line goes high, the side where 0 is stored discharges, and the side on which 1 was stored does not discharge because the bit lines were already pre-charged to high. There is no VDS across this device. So this doesn't discharge. The differential that appears between the bit line and bit line bar is then amplified through a circuit known as sense amplifier in the IO region. This appears to be very simple operation, doesn't it? However, it's not as simple in the sense that there are challenges involved. The first challenge is that of stability. See, when we say that there is a 0 stored here and we take word line to a high level, what we are essentially meaning to say is that some current will flow due to which bit line will discharge. Now, for flow of any current to happen, this 0 has to go to some value other than 0 so that there is some VDS across this device, the pull down device. Otherwise, there can be no flow of current. What that means is that when we are reading, there is a kind of a potential divider that is getting formed between bit line and ground voltage. You do not want Vx or the node at the voltage at this node to go very high, else the latch would flip. The contents of the memory cell would get corrupted. So to ensure that the stability of the cell is maintained, this resistance should be high. That is, the excess transistor should be resistive. Now that is one criteria or one need that we have. But we also want to improve performance. What that means is that the read current needs to be increased, which means that the excess transistor should be more conductive. At a different level, we may also say that the capacitance needs to be reduced, so the excess transistor needs to be smaller, or we could use hierarchical bit lines or word lines, architecture level solutions to achieve high performance. But do you realize that over here we have conflicting requirements? We also want to have the excess transistor become resistive, while at the same time we want it to be more conductive. So how do we handle it? We will see. Let's first look at the write operation also. When we want to write into the memory cell, now as you notice, initially we have a 0 written on this side and 1 written on the other side. When we want to write the other data, so what this means is I would probably want to write a 0 on the other side and 1 on this side. So what we do is we take the side on which we want to write a 0, the bit line on that side to 0. So BL remains at 1 while BL bar has gone to 0. Now, when the word line goes on, the internal node over here discharges through the bit line, and then after this has discharged, the other internal node gets charged to 1, and that is how the write operation happens. This also appears to be simple. However, there is a challenge here too. The challenge is that we want to be able to accomplish this write operation successfully. We want that any current that is coming from this pull-up device should be less than the current that we are discharging through the excess transistor. So there is a ratioed sizing of the pull-up device and the excess transistor that is required. In fact, this pull-up device, in most advanced technologies, you will notice that this pull-up device is probably the most resistive device that you will make in the technology. This device not only has the minimum width, but also has larger length than the minimum length prescribed by the technology. So this is a very resistive device. An immediate consequence of resistive device, resistive PMOS, is that when I need to charge the other node to VDD, this PMOS is weak. Essentially, this has a direct impact on write time, that is the speed of the memory. So again, we have a conflicting requirement where we want the pull-up transistor to be resistive, but for performance purposes, I want it to be more conductive. The way to handle these kinds of conflicts has been two-pronged. The first has been people have proposed different topology cells, different cell topologies. If you open IEEE Explore and just search about SRAM cells, you will see SRAM cell topologies 60, as I just told you. You will also see denser topologies, but to reduce the complexity of the cell, or complexity of operation, you will see there are topologies proposed from anything from 7 transistors to 18 transistor memory cells. This obviously means much larger area. If 70 to 80% of your die area is SRAMs, putting larger area is, shooting yourself in your foot. In my lectures on SRAMs at IIIT, I very commonly tell my students that, for VLSI, area is gold. For VLSI designers, area is gold. You just don't want to lose any area. But for SRAM designers, area is diamond. It is absolutely prohibited to give up area in SRAMs. So while there are these topologies of 12 transistors or 18 transistors or 14 transistors or anything like that, larger area is actually a big no-no. So what is usually done is that we apply what are called as electrical read and write assist schemes. See, did you notice I did not say that you have to have a smaller excess transistor or a larger excess transistor? I simply said we need to make them more resistive or less resistive. Since these are transistors and they are controlled transistors, we have the control gate with us. We can electrically modulate their behavior. We can electrically change their characteristics to make them more resistive or less resistive. So these electrical assist schemes are applied onto SRAM arrays to enable successful read and write operations in advanced technologies. Some of the common read assist schemes are word line underdrive, in which case the word line is not taken to a full VDD level. Now, what would happen if you do not take word line to a full VDD level? The pass gate will become resistive. The excess transistor will become resistive. As the excess transistor becomes resistive, your stability improves. But what goes for the toss? The read current. So the performance goes for a toss. If you don't want to do that, then what you can do? You can, instead of giving a continuous word line, you can give pulsed word line. So give multiple pulses of word line where word line goes to full VDD. In which case, while the cell starts to become unstable, you've disconnected the word line. So the cell becomes stable again. Then you turn it on again. It discharges the bit line further. Then you turn it off before it starts to become unstable. Complex. But yes, it's a read assist scheme which is proposed and probably also used at some places in the industry. Pre-discharged bit lines is another scheme where we say that the voltage that you apply across the potential divider of excess transistor and pull down in itself is less, which ensures that the noise injected into the memory cell is reduced. Similarly, you have regenerative sensing in which the sense amplifier writes back into the memory cell. You have supply boost, power intensive scheme, and negative VSS schemes also. You will notice that for write operation, so while for read operation, for read assist, we wanted to underdrive the word line. For write operations, we want to give a boost to the word line so that the excess transistor is faster. You are able to, so that the excess transistor has more strength than the pull-up. So they are contrary to each other. When you want to read and ensure stability, you want word line to be underdriven, whereas when you want to read, the word line needs to be boosted. The most commonly used write assist scheme, though, is negative bit line. So bit line is taken to a level lower than 0 so that you can successfully accomplish the right operation. There are also schemes like multi-level modulated word lines where the word line is initially underdriven. You wait for bit line to discharge a bit, then you overdrive it and you ensure that the right operation completes. There are schemes like supply lowering, data dependent body modulation. So in technologies like FDSOI, you can also control the fourth terminal of the device, which is the body terminal, and that can give you a significant advantage and speed up. If you design the cells, if you design the memory cell well and use the appropriate technology levers, you can see that the body modulation can be a cheaper technique than, for example, modulating the supply voltage in terms of VSS or the bulk otherwise. Okay, so with new levers coming in, you have more ways to assist read and write operations inside the memory cell. The story doesn't end there. I believe many of you must have seen this kind of a distribution. This is the famous Gaussian distribution. What it says is that any random process, if it's a natural process, can be described through a Gaussian distribution, through a distribution which is Gaussian in nature. We have a mean value of the distribution, which is where we probably targeted our operation, our manufacturing process. And then the distribution is characterized by the standard distribution and the standard deviation. And for a Gaussian distribution, within plus minus 1 sigma of the mean, we know that 68.2% samples exist. Within 2 sigma, we have more than 95% of samples. And by ensuring that we are qualifying the design plus minus 3 sigma, we ensure that 99.7% of the samples are well taken care of. So do you think this is sufficient when we talk about SRAMs and the read and write operations in SRAMs? Let us just put in some numbers. If I say that the typical on-chip capacity of an SRAM is of a on-chip SRAM capacity on a chip is 1 megabit. Now 1 megabit is too small. You already, like in advanced technologies like 7 FinFET or 14 FinFET, you already would see that on-chip a typical digital SoC would have an on-chip memory which is greater than 32 megabit or 64 megabit. But let's for now just assume that we have 1 megabit on-chip capacity. So how many memory cells are we talking about? Okay, for the sake of simplicity, let us say 10 raised to power 6. So there are 10 raised to power 6 memory cells, and if I qualify stability criteria for plus minus 3 sigma of the cells, the failure rate is 0.3%. Am I right? So 0.3% of cells would fail. Sounds to be very less. But what that means in terms of a 1 megabit SRAM capacity is that on every die, you will have 3,000 failures. So your chip yield will be 0%. This is absolutely unacceptable. So if you just put in these numbers, you will see that to qualify anything like 16 megabit or higher, you need to have at least plus minus 6 sigma qualification on your read stability criteria and writability criteria. Plus minus 6 sigma. Let it sink in. If you want to verify any memory circuit for plus minus 6 sigma of variations, how would you verify it? See, the typical statistical analysis methods involve Monte Carlo simulations. If you put random variations on, say, VT and mobility of all the devices and see the impact on parameters of interest, for example, over here, noise margin or writability, you need 30 to 60 simulations to validate within 1 sigma. Okay. If you want to validate 6 sigma or plus minus 6 sigma, you will need more than 1 billion simulations. This is not a cost that you as a designer can pay when you are iterating and designing the memory cell. So specifically for SRAM design, there have been, and there are current, there is also ongoing research. There is the concept of, for example, importance sampling, where after the first few initial simulations with random variations, we estimate the sensitivity of the output parameters to the input variations. And then we learn on the fly and continuously aggregate the variations to achieve risky samples. So while over here, I said that you will need something like 10 raised to power 9 samples, when you go to importance sampling, you could probably do with 10 raised to power 4 to 5 samples. To talk of plus minus 6 sigma qualification. That is also not a small number. Can we do better? And for that, there are still more advanced methods, which are based on what is called as design of experiments, in which inputs, the input variations are given sequentially one by one, and their impact on the output variables, output parameters is observed. And we estimate the good functionality contours in terms of sigma extents, where we say that, and practically so, the VT variations across different devices inside the memory cell are independent of each other. So we say that the variations of VT across the devices are independent, and we just do a root mean square sum of these variations, and we then integrate it to estimate the yield. When you go to DOE kind of an approach, you could probably do well with something like 10 raised to power 3 samples. Do you see, are you able to sense the kind of impact even CAD validation schemes could have on design cycle time? It is the intelligence for SRAM designers. The intelligence need not go only in sizing the devices or only in ensuring some parameters, 4 or 5 parameters around the memory cell. As an SRAM designer, if you intend to become one, you also need to look at various other aspects, including verification and how to speed up that verification. In fact, I would not say only an SRAM designer. Any memory designer would need to look into all these aspects. Let me take you through another journey. In SRAMs, we also have what is called as a replica path. You remember this figure that I showed you just a little while back, where we said that the clock would come and we would generate the word line, the differential would appear, and we would activate the sense amplifier. In my previous part of the discussion, I had consciously not talked about what would activate the sense amplifier. See, the sense amplifier is an analog circuit, is an amplifier which has its own offset. To do the correct read operation, it is necessary that the differential that appears on this pair of bit lines is higher than the offset requirement of the sense amplifier. What that means is that we need to somehow track the worst case cells. You know, this cell would probably be selected last in terms of word line selection and would have the longest delay before SAN arrives. So what we do is we add what is called as a replica path to track the worst case. The output of the replica path is used to trigger the sense amplifier. A key design optimization or a key design verification that is required is that this SAN arrival should happen only after there is sufficient differential appearing on the bit lines here. Graphically, I can represent it like this. This is the differential voltage distribution from the bit lines. And this is the sense amplifier offset requirement. What is essentially required is that the minimum differential voltage that appears on the bit lines should be greater than the sense amplifier offset requirement. This would ensure that there are no failures. However, as the technology is scaling, what happens? The mismatch increases. As mismatch increases, what happens? The sense amplifier offset requirement increases. As technology scales, there is another thing that happens. The memory cell also shrinks. As the memory cell shrinks, the current that it can drive reduces. So we see that the differential voltage distribution curve starts to come closer to the sense amplifier offset requirement. But that's not all. While the current reduces, the mismatch increases also for the memory cell. What does this mean? This means that there is yield loss that will happen. We don't want that to happen. So what do? You try to push this curve out. How do you push this curve out? You can push this curve out by adding more delays into the replica path, where you say that you will trigger the sense amplifier a little later. When you trigger the sense amplifier a little later, this curve naturally shifts a little to the right. But that means performance goes for a toss. Tell me one thing. When you purchase your new laptop or your new cell phone, do you expect that the performance of the new laptop or the new cell phone would be worse than the previous generation one? No. As a consumer, we want whatever new electronic products we purchase, they should operate faster and more efficiently than the previous generation products. So we need to do something about the verification approach also. So in our team, we actually observed that the distribution actually, this edge which we have assumed Gaussian till now is actually not Gaussian. And in fact, we could actually achieve better yield than what the Gaussian assumption proves or what the Gaussian assumption gives us. And therefore, we need to go into advanced statistics of what is called as extreme value theory and look at what is the minimum current in a particular bit slice that is engaging with a sense amplifier. By use of extreme value theory, that is advanced statistical methods, we are able to recover yield at faster performance. So we were able to demonstrate that you could improve performance by up to 7% by just changing the verification method. So as a SRAM designer, you need to look into various aspects of memory design, not just sizing the circuits. Now, that was still SRAM design. And now I come to the last part of my presentation, where I want to share with you the need for what we call as in-memory compute these days. See, von Neumann architecture-based processors access memories when they need to do some computation. So the memories are accessed for getting data. The compute happens in the processor, and then the data is sent back to the memory. Let us say we wanted to do an operation of A plus B is equal to C, or C is equal to A plus B. What do? You give the first instruction. You say load A. The instruction goes to the SRAM, and the SRAM sends data into the processor. Then you give the second instruction. You say load B. The second instruction goes to the bus to the SRAM. SRAM sends the second set of data to the processor. The processor does the addition path, a new data is generated, and then you launch another instruction, which then sends another set of data to the memory for writing operation. So for just one instruction, we needed to interact with the memory 6 times. As we go into big data applications, as we go into applications like neural networks, large scale GPU, big GPUs, and so on, there are so many instructions and so many data interactions that the throughput of your processor gets limited by the bandwidth that the bus offers you. This limitation of bandwidth is referred to as von Neumann bottleneck. How do we find a solution to it? The solution around it is what we call as in-memory compute. If we have an in-memory compute capable SRAM or a memory, all that this processor needs to do is it needs to give the instruction C is equal to A plus B. The memory would access location A, access location B, generate the output C, and then automatically store it at a location C inside itself. The kind of interaction required through this bus reduces so significantly. So now your entire throughput improves. The power that you would have wasted in transmitting data to and fro from the memory to the processor, that is saved, and you have a much more efficient memory system. That is what is in-memory compute. But what does it require? To enable in-memory compute, you clearly need to have an advanced in-memory control engine. You also need to see which functions to implement inside the memory. It's not very simple. While add, subtract, and probably multiply operations can be easily implemented inside the memory, convolution involves much more juggling. Then there could be some application dependent function also. For example, an image processor would require something like a transpose function or a shift function or a complement function. You would need compare functions, you would need shift functions, you would need rotate functions, and so on. So which of these functions do you want to put inside the memory is a question that you have to ask yourself when you want to enable in-memory compute. Another key question to ask is, do you really need to put the function inside the memory? Or can you just place it somewhere near the memory? If you still place it near the memory, you do not need to access the processor. And you still are able to bypass the von Neumann bottleneck. These questions are not simple to answer. They're not simple to answer, but there are many more questions that need to be answered. For example, do you want single bit operations or multi-bit operation? Do you want serial compute or parallel compute? Answers to each of these decisions has an important impact on the power, performance, and area of the entire system, compute system that you are building. Whether you want to play fully digital or you want to go to analog and mixed signal mode, all these things you as a designer need to take care of. So while there are these many questions, are there any answers also? We are working to find answers. Numerous experiments are happening. If you look at any recent publication, recent runs of the conferences like ISSCC or VLSI Symposium or anything, you will see there are full new tracks on in-memory compute. There are innovations which are about bit cells. We talk about read and write decoupled cells. Again, you increase the size of the memory cell. You go to 80, 90, 10T cells, even bigger ones. You are also talking about capacitively coupled cells. Again, 8T with capacitive coupling to 10T with capacitive coupling, 12T with capacitive coupling. And you will notice that each of these schemes has its own benefits. Twin 8T cells enable 2-bit weighting, 2-bit weights inside your memory cell itself. Transpose 8T cells have been proposed to enable cross-point computes and even transpose functions, for example, for imaging applications. So many more innovations are happening across the storage cell. And when Manan will take over, he will talk about more innovations in the non-volatile domain and how non-volatile memories are also innovating on the memory cell and the cross-point computations to enable faster, more energy efficient computes. There are innovation happenings on the row decoder side also. A row decoder was always considered to be a very simple circuit, a simple address decoding circuit. But today, it's not just that. When you talk of in-memory compute, you need to talk about parallel row selection to increase the throughput. There are experiments about changing the word line on duration, again to enable multiple bits, so that the word line on duration is dependent on the feature vector that you want to calculate. Dynamic pulse word lines, again enabling multi-bit. How many pulses you send on the word line would define how the bit line would discharge. Analog levels on the word line, again to enable multi-bit, where the level of the word line is dependent on the feature vector. And so on. So many more experiments are happening. There are also innovations happening on the bit line and the sensing side. Very commonly, you will see that bit lines are used as accumulators. DACs are being used for weighted bit line pre-charge. ADCs with weighted capacitor banks are being integrated into the memory. So the simple sense amplifiers, latch type sense amplifiers, no longer work. You need to add much more to that. Simultaneously, there are also architecture level innovations. For example, for signed bit computations, there are separate bit lines for addition, subtractions, different parts of the array, or a bit slice doing these different computations, and then some logic in the IO periphery to merge them. Different bit slices for doing different multi-bit computations. Again, bit serial parallel compute paradigms, loading of feature data and weights inside the memory. A lot of things are happening, and no wonder we also are seeing a wide range of results. Early on, initially, something about 4 or 5 years back, people were only looking at TOPS per watt as a figure of merit. And you would see that there are, TOPS per watt range from 28 to 351. And mind you, they're not technology dependent. Or while this figure is technology dependent, it is not that 28.1 at 65 would translate to a higher value or 130 or a lower value at a lower technology node. Just technology scaling could give you some benefits in terms of TOPS per watt, but you will notice that architectural changes can give you bigger benefits. In more recent times, TOPS per millimeter square was also introduced, because we noticed in the previous section that there are many architectural decisions that could have an area impact when you talk about improved performance. This is not all. You will see that when you look at more papers, you will see that people are talking about TOPS per watt performance of more than 600, 700 TOPS per watt. I've also seen papers exceeding 1100 TOPS per watt. And there are comparisons across different domains where we also bring in terms of what kind of configurability or dimensionality your solution offers. So all these decisions that you make about in-memory compute can have a significant impact on the final system. No wonder the jury is still out. We do not know what will be the final set of architectures of in-memory compute that will be there in the industry. The industry is still just looking with awe and curiosity as to where the things are settling. But the field is still very raw. A lot of research is happening here. And in fact, I myself have 3 students working on in-memory compute as of now. So with that, I kind of close my presentation. If there are some questions, I will be happy to take them up.
Ishita, are there any questions for Dr. Grover?
So I see one question, which is about how the peripheral and bit cell design changes or trends when the node moves to FinFET technologies. So the FinFET technologies are for real, and you already have FinFETs in your cell phones today. You still have 60 cells. You have all these various variants of cells also, but 60 cells are still the most commonly used. The peripheral circuits have also evolved a bit, but there are other challenges that come with advanced technologies, which were not there in the earlier ones. For example, new kinds of post-layout effects start to appear, new kinds of things like how do you dissipate the power in a 3D setting, how do you apply body modulation in a 3D setting, and so on. So wide range of those things are appearing and solutions are evolving to handle those challenges.
Thank you for the answer, Dr. Grover. Are there any other questions? I can't see any. All right, good. So I would like to extend special thanks to Dr. Grover for this enlightening lecture. It has opened up quite a few doors for me too, and I hope to collaborate with him to do good things in the future. It's quite exciting.
Thank you, Professor Kaushik.
I would like to now invite Professor Manan Suri. Dr. Suri, over to you.
Thank you, Professor Saha. Thank you, Professor Grover. Taking over from Professor Anuj, I will cover the second part of this tutorial, and here I'll be focusing more on NVM, emerging NVM, and some case studies or some recent R&D examples of in-memory computing, or how do we compute with memory specifically on the NVM side. That is what I will cover in this session. So I'm at IIT-Delhi in the electrical department, and as Saha also mentioned, I run the NVM and neuromorphic hardware research group. So we look into several NVM and memory related topics. So I can be reached at this email ID, or you can look more about our research on this link. So I'll get started. So this is the organization for the second part of the tutorial. I'll cover some basic motivation, some things in the motivation Professor Anuj already covered before me. He mentioned about the importance of non-volume computing. So similar motivations, similar use cases exist for why we are looking into this. I'll also try to lay some motivation, why even pay more attention to emerging NVM, and then we'll take up PCM or phase change memory as a case study. We'll go through some basics because this is a tutorial. We'll see how PCM devices work, which is an important class of emerging NVM devices, and then I'll briefly touch upon some computational case studies of these NVM devices, and then we'll conclude. So I always like to start with some context, and if you look around whatever is happening around us, we are essentially trying to build digital empires around in our lives, whether it is things like IoT, healthcare, defense and security, smart cities, social media. All of this is like just generating more and more data, and the requirement for processing the more and more data that is collected to draw insights from it or to make sense of that data, right? So one direct offshoot of, or one direct consequence of this massive digitization or living digital lives is the fact that you need something to store all this amount of data. So just the sheer volume of data that is projected to grow or is already growing, the media or the platform on which you host or store this data is NVM, right? That's non-volatile memory. What used to be your tape drives or hard disks a few decades ago is now we are crossing flash and new emerging NVM type devices. So that is one basic motivation for the increased activity in the domain of NVM or different types of NVM or emerging NVM, from the viewpoint of pure storage, that as the amount of information grows, you need better means, you need more advanced means, more compact, more high performance, low cost means to store. Okay, so that is the baseline motivation for why NVM is becoming important with every passing day. Now, a slightly, secondary consequence of this massive information is that the moment you have this information, you are in the need to process it efficiently. So what is happening in industry, academia, and R&D all around the globe is that there is a lot of effort and consensus that if you want to efficiently process this huge amount of information, you will need dedicated hardware. It's no longer, we are no longer in days where generic hardware can do many things, but then it does not give you the ROI or the benefits with which the computational performance or the merits are not that high with generic hardware. You need dedicated, very specialized hardware for your data intensive workloads. And these workloads can be anything like your deep neural networks or your standard ML or any kind of analytics or processing, the recent trends is that dedicated silicon is coming around, and there are various cases. I took some, interesting cases over here. Obviously, the GPUs are the more common ones among all of these. Then there are things like neuromorphic chips, neuromorphic servers, going to wafer scale chips, things like TPUs, and another spiking neural network hardware and so on. So there is good evidence to say that the kind of application domain that is dominating these days requires dedicated hardware and specialized architectures. And a lot of these architectures, they are also coming from the non-von Neumann inspired computing. What Professor Anuj mentioned with the nice animation in the previous presentation, that you want to minimize the communication between the processor and the memory. So once you start working, with these kind of platforms, what you see is that in these dedicated architectures, if performance is the goal, memory starts to take a center stage, and NVM particularly becomes even more important. And again, this is important because of two reasons. The first reason is the more obvious, that they have to hold more data. So that is the basic storage or density reason. The other reason comes from the nature of compute or the nature of workload or the math, the kind of math that these processors or specialized processors are trying to do. And there also it is seen that memory, it is ultimately the memory which will make or break your performance, and not so much logic or not so much the core CPU compute or the core processing unit. So just for instance, if you look at this chart does a dissipation breakdown of one typical CNN, and you would be quite surprised to see that almost 90% of this breakdown comes from memory related actions, and pure compute is just 10% of it. So that means there has to be a focus on the technology that goes to build your memory components, the memory subsystems, whether it is on the storage side or more on the cache side, or whatever kind of architecture you have. The memory becomes really important. And then there is more evidence in literature that what is the data shuttling cost when you go between compute and memory, and so on. So these are the two primary motivations which really make it important for all of us to look at NVM in a different sense, or with a lens which is beyond just density, with trying to ask ourselves that it's time to start asking for more functions or more functionality from memory rather than just storing ones and zeros in it, right? And that is somewhere where you also get the seeds for in-memory computing or memory-based or near-memory computing and things like that. So that brings us to the need for investigating NVMs. And when we talk about emerging NVMs, so this is basically the class of nanoelectronic devices which are essentially two-terminal, which have some new unconventional materials. They have new underlying physics, and which leads to some new opportunities. And there is a whole bunch of different technologies depending on what kind of materials or underlying physics you use. There are devices like CBRAM, which stand for conductive bridge RAM, oxide-based RAM. You may have heard of terms such as memristors, RRAMs, resistive memories, phase change memories, STT, spin transfer torque, or there are cases where you combine one or two effects and you end up with some hybrid kind of memory devices. So there are things like ferroelectric, some special charge-based devices. So this is a whole gamut of different technologies which are becoming relevant, which are basically beyond flash, beyond going your NAND flash, beyond your charge-based flash technology. And once you get into 3D flash or new materials, that is what starts getting termed as the emerging NVM technologies, or the emerging resistive NVM technologies, to be more precise. So while There are several different flavors of them. There are also many commonalities. The first one being that most of them are two-terminal, and as there is always, a pair of electrodes and some active switching material sandwiched between these electrodes that helps you realize the memory functionality or the storage functionality. So, for instance, when the materials are solid electrolytes or with a sacrificial electrode, the kind of underlying physics that drives this memory operation, it's more close to redox reactions. It's like an electrolytic cell. So that is where you get a conductive bridge RAM. When you play with the vacancy and defects, when you manipulate the vacancy and defects, more electronic effects in your switching layer, you end up with devices like SRAM. When you actually change the phase of the material between amorphous and crystalline phase to realize storage, you end up with a technology such as phase change memory. So we'll go into more details of PCM in today's session. And then when you have magnetoresistive effects at play, then you have things like MRAM, STT, and so on. Okay, so let's begin with PCM. So PCM is, the interest is continuously growing, and this is a slightly older graphic. This goes from 2000 to 2010, and it shows a consistent increase in the domain. And if you were to observe this chart beyond 10 to going for the next decade, I can assure you that it is going constantly up. So there is a lot of effort both in academia, R&D, as well as industry. There are several use cases to pursue the technology. Okay, so brief trivia about PCM. So from the conceptual viewpoint, the concept of phase change to realize storage has been around for a while. It's not very new, even though the electronic PCM devices get classified as emerging NVM technology, but the base underlying concept or the broad physical concept has been around for a while. And one of the most successful or classic cases for phase change based storage is coming from the traditional storage, which we all have used quite extensively, which are CDs, your compact discs, or your DVDs. So your optical storage media, is already based or already works on the principle of phase change, where you create amorphous or crystalline phase, you encode your zeros and ones, your digital information in the form of different phases of the material, so it is the concept has been there around. Now the key material that helps to realize this phase change phenomena is known as chalcogenide or chalcogenide chalcogens. These are the phase change elements where we manipulate them to transition them between amorphous or crystalline phase. One key figure behind the electronic PCM devices or having electronic PCM devices as of today, Stanford Ovchinsky, an inspiring inventor, came up with the first electrical insights onto the possible use of these devices for storage as early as 1968. But the postulates or the concepts that he came around as early as that time were quite useful, but they could not be put into practice pretty much till the early 90s, because essentially what was limiting from the concept stage to a technology realization stage was the state of lithography or the state of semiconductor fabrication. And as there was a shift as there was a progress in the lithography from 10 microns to 180 nanometers or sub-micron scale, that is when really it became possible to translate some of these early concepts into real devices. And you pick up any company, whether it is Micron, Hitachi, IBM, Samsung, you will see a lot of industrial activity also happening along the lines of PCM devices over last several years. Both for storage as well as embedded NVM, PCM has been widely explored by industry. A lot of industrial investment has also gone into it. So let's go into the materials and see how this thing works. So chalcogenides, these are if you look at your periodic table or the chalcogens, they must include either sulfides, selenides, or tellurides. So we are talking about different compositions or stoichiometries of elements such as sulfur, selenium, tellurium. So that is essential to start walking towards your phase change materials. Now, one of the most common, or let's say gold standard in some way, material for electronic PCM devices is known as GST. So that is the short acronym. And GST is essentially germanium, antimony, tellurium in the stoichiometry 225. So now there is a lot of science and effort or engineering, lot of material engineering behind arriving at this stoichiometry, taking care of what properties, reliability, and trade-off the device exhibits. So it's not just by chance; it's very carefully engineered. But what you can take away is that this is one of the most standard classic textbook PCM device material, GST, in the composition 225. So most of your PCM studies are would be it won't be incorrect to say that 80% of your PCM studies would be centered around electronic PCM device studies would be centered around GST. Now let's come to the storage concept. So the chalcogenide material, its amorphous phase has high electrical resistivity, and its crystalline phase has low electrical resistivity. So if you have high electrical resistivity in a phase, you can exploit that, or you can exploit it as a resistive material. Less current would flow through it, and if you transition the material into a crystalline phase, it will become more conductive, and more current would begin to flow through your device made up of that material. So this basic difference in the amount of current that can flow through the two different phases, or the amount of current that you can easily sense flowing through two different phases of the material, is essentially what gives it the power to store, or the power to store 0 and 1. So traditionally one would encode the amorphous phase as a high resistance state, also referred to as HRS, high resistance state, or a 0, and similarly a crystalline state, one would refer to it as LRS, low resistance state, or 1. So that is the basic principle of storage in these devices. And just to let you know that these phases, they are stable and they are non-volatile, meaning if you program the device in a specific state, it would stay in that state for a fair deal of conditions, for a wide range of time and environmental conditions, and that is how it becomes non-volatile. So in fact, there are many materials in which you can induce phase changes, but if those phase changes are not stable, if they are not energy efficient, and if it is not ensured that they would stay in that state under certain operating or environmental conditions, it would not become industry grade storage or industry grade non-volatile memory. So most of the material engineering goes to ensure that after the phase change, the phases are reliable and stable, so that your zeros and ones that you're storing inside the technology, they remain safe. Now, the optical counterpart just exploits another property, which is reflectivity and not resistivity. So coming back to your CDs or DVDs, when you create amorphous region on the backside of your CD or DVD, it would have a low reflectivity, and when you create a crystalline spot, it would have high reflectivity. So in your optical discs, you use a laser, you shine a laser on the backside of the disc, and you check what is being reflected from there. And so whereas in this case you would use currents and voltages and see how much current is flowing, or what voltage you can sense at a resistance across the device. So in the optical counterparts, you would see what is being reflected from the material. So let's go a bit further into the working of these materials. So how does one realize amorphization, or how does one actually amorphize the material? The key here is that when you're trying to amorphize the chalcogenide material, or when you're trying to create amorphous region, you need to melt the material and then you need to quickly cool it. So the important terms here are melting and quick cooling. So melting means you need to cross its TM or its melting temperature. You need to provide sufficient heat to it. And quick cooling is very important here, meaning the cooling should not be, so this is a relative term when we say quick cooling. So at a atomic level or at a material level, what you're trying to do is after melting the material, you're not giving it sufficient time to rearrange into a crystalline structure. You're abruptly removing its temperature profile, and so it doesn't get sufficient time to reorganize itself, and you end up with a disorganized or less organized amorphous structure. So that is the basis behind amorphization. Whereas in crystallization, what you do is you slowly quench or you slowly heat the material over a longer duration of time. Again, when we say cool quickly or heat over a long duration, these quick and long, these are relative terms, and these are time scales in context of the material. So quick cooling here might mean 50 nanoseconds or few tens of nanoseconds, and long heating or slow cooling might mean something like a millisecond or a few hundred microseconds. So these are the quick and short scales that we are referring to. So when it comes to crystallization, you are essentially heating the material at a critical temperature, which is known as above a critical temperature known as crystallization temperature, but definitely below the melting temperature. So the melting temperature would be higher than the crystallization temperature, because if you cross the melting temperature, there are chances that you may start the process of amorphization. So you stay somewhere between TC and TM. Now, crystallization in itself is a complex physical process. It involves other intricate processes such as nucleation and growth. And what this chart shows you is the appearance of some crystal nuclei or crystalline nuclei inside an amorphous mass. So the yellow here is an amorphous region in a chalcogenide, and the green is the crystalline region. So a nucleation dominated material, when it begins to crystallize, it would have the way how it would crystallize would be dominated by appearance of these crystal nuclei. So predominantly more and more crystal nuclei would appear, and that is how the amorphous region would get converted to crystalline. There is another class of materials which is known as growth dominated, and growth dominated materials would, what it means is that whatever few nuclei are there, they would grow into complete crystal structure, and they would predominantly crystallize because of the growth of the nuclei and not because of the number of the nuclei. So for crystallization, both these processes need to go hand in hand. You need nuclei and you need those nuclei to grow. But if your crystallization is dominantly happening just because of the number of nuclei, it's nucleation dominated. That is a qualitative way to look at it. And if it is happening dominantly by the speed with which a crystal grows, it's growth dominated. Okay? So this is one aspect of the crystallization physics. So let's go further. So now, in terms of your storage, when you're storing 1 or 0, or you're transitioning between the two states of the device, then the speed with which the material goes from amorphous to crystalline state or vice versa will determine how fast you can switch the device, or how fast you can encode data or store data in it. So crystallization of the amorphous phase change material is a process that determines the data rate in your or the speed or the latency or the write latency of the technology. So that is also where the material engineering goes to improve the latency or the speed of the device. You need to focus on how fast you can crystallize. As mentioned, crystallization would involve nucleation and growth. So both these parameters need to be optimized. And again, within nucleation, you have more flavors. There can be things like homogeneous nucleation, which occur in the bulk of the amorphous material, or there can be nucleation happening at the interfaces, which is known as heterogeneous nucleation. So both of them would have different consequences or different underlying factors which drive them. Now, this is a more real sample. What you see on left is a nucleation dominated material, what you see on the right is a growth dominated material. So both had some amorphous spots. So both of them had 9 amorphous spots, these 9 circles that you see, and then an attempt is being made to crystallize them. Okay, so the crystallization, the nucleation dominated material, you can see how crystallization progresses in it. It progresses by the appearance of more and more nuclei. So this is how it would look. And the growth dominated one, it progresses, the crystallization progresses by the expansion or the growth of a few crystalline nuclei which were at the interface. So this visually illustrates what I was trying to say on the previous slide at a material level. And then the quantifiable parameters to optimize this physics for the nucleation, there are things known as nucleation rate, that is the quantitative metric, and for growth there is thing known as growth velocity. Now what makes this further complicated is that these parameters are temperature dependent, and now you would have understood that for the PCM devices we require some sort of heating, right, either crystallization or melting. So there is a temperature, and that temperature is also bound to change, and then the underlying physical parameters are not constant with temperature, they are linked to that temperature. So this makes it a very complex and cyclic physics to analyze, and that opens a lot of scope for optimization and challenges in the material science that goes behind PCM devices. Okay, so just as I mentioned that GST is a nucleation dominated material, there is another chalcogenide used for this technology, GESB, in the ratio 15:85, which is a growth dominated material. So this is the growth dominated example. This is a nucleation dominated material. So let's move to the electronic PCM devices. Now the structure that I'm showing you here is a typical lens type PCM device, also known as a plug type PCM device or a mushroom type PCM device. And how this structure is designed is that you have 2 electrodes. You have a top electrode and a bottom electrode. Below the top electrode, you have the chalcogenide switching layer, which is GST. And below that GST layer, you have a heating plug or a heater plug. Mostly, it is made up of tungsten or some other electrically conductive material. So it is like an extension of your electrode. And then you have some, separators or insulators around your plug. So the device itself, the PCM device itself, when it would sit in an array or when it would sit in an architecture, it would sit there with some kind of selector device or some kind of selection device. And this can be a transistor or this can be a diode. So the configuration of a bit cell of your PCM device is known as 1T, 1R, where T stands for transistor and R stands for resistor. Because when you program this PCM into a crystalline state or amorphous state, after programming it, it is essentially a resistor. So we call it 1T, 1R. So this is the bit cell, just how you saw in the previous session. The bit cell of your SRAM would involve 6 transistors. It is a 60-bit cell. Here you have a 1T, 1R bit cell, and then you start making arrays by repeating these cells with your periphery, your decoders, sense amplifiers, and so on. So this is the device from inside. Now let us go into the working of this device. And as I mentioned, there are 2 temperatures, crystallization temperature and melting temperature. So in order to crystallize the material, if you start from an amorphous region, you need to heat it with a certain temperature profile that's slow, relatively slow, and that cools down slowly so that it is giving sufficient time for the material to crystallize. And it is between your melting and crystallization temperature, meaning it is above crystallization, but it is not as high to cross your melting. So this kind of temperature stimuli would lead to creation of low resistance state or would lead to programming the cell to a state 1. On the other hand, a temperature profile or an electronic stimuli which crosses the melting temperature and then quickly cools down, doesn't let the device rearrange itself, would lead to creation of a zero or a high resistance state. So this is your reset pulse and this is your set pulse. While this is on the y-axis, you have temperature here. These structures are engineered, the device structures are engineered in such a way that when you apply an electronic voltage or current pulse, whatever is the shape of your electric pulse, it would create a similar shaped temperature profile in your chalcogenide material over here in the GST material. So you indirectly try to create this temperature profile through your electronic pulse. So your reset pulse would be of this shape and your set pulse will be pretty much of this shape, which would lead to crystallization or amorphization in the technology. That is how to program it into 1 or 0. Okay. And what happens, this tungsten plug, which is also known as the heater, let me elaborate a bit more why we call it the heater. So the assembly that you have over this layer, you do two forms of engineering. Not only you do electronic engineering here, you also do some thermal engineering, because what you want to do is you want to maximize your heat dissipation in the chalcogenide interface for efficient programming. So while building this structure, you would choose materials which don't allow escape of heat or in unwanted directions, and heat concentrates at a specific spot to have low energy based programming. And you may be wondering where this heat is coming from. It's because of Joule heating effect. This would have some resistance. Your heater plug would be chosen in such a way that its I square R or its heating effect creates temperature profile at the right place. So it's Joule heating driven temperature manipulation of the chalcogenide layer that leads to T melting or T crystallization. Okay. Now let me ask a question, just to think about. Let's say you start with a crystalline, you start with your PCM device when it's in the crystalline state, and then you apply some electronic stimuli, some pulse, and you try to, through Joule heating, you're trying to increase the temperature of your phase change layer. Now, if you cross the T melt, you can cause melting and you can create amorphous region. But if the material is already in the amorphous state, which means the high resistive or the insulating state, then how can you ever crystallize it? How do you go back? Or how do you switch it back? I'll just use this figure to make it more clear what I'm trying to say. So, when the device is in crystalline state, this PCM layer, if you look inwards, either from the top electrode or the bottom electrode, if you try to make a circuit diagram of all these elements, you would have this PCM layer. It would look as a resistor with low resistance. However, in the amorphous state, it would be very high resistance, almost non-conductive. So you don't have any path for current to flow through this entire stack. So if no current can flow through this entire stack, how do you think, any idea how do you ever achieve the Joule heating and subsequent crystallization? So what I was saying is that when you are so let's say you start from an amorphous state. So in the amorphous state, the device is non-conductive, and as you keep applying increasing stimuli, you would see that the current would not increase. If you are in the crystalline state, it would act as an ohmic resistor, and as you are applying more and more stimuli, whether in voltage or in current, more current would flow through the device, and that can lead to Joule heating, which can subsequently lead to crystallization or melting. So the key here, while starting from the amorphous state, is a special phenomenon known as OTS, or Ovonic threshold switching. So what happens in Ovonic threshold switching is that even while staying in the amorphous state, the material after a certain critical field suddenly becomes conductive. So this second track, so this is also known as a snapback effect, because the current curve is snapping back. So you can see over here that as in the amorphous state, initially the current is very low as you're applying stimuli to the device, and then suddenly there is a shoot up of current. So this is a second type of change that happens in phase change materials, which is known as OTS or Ovonic threshold switching. However, a key point to note here is that this change is volatile. This is field driven, E field driven. So the moment you disconnect the bias or you remove your stimuli, the amorphous phase would again come back to the low conducting amorphous phase. But if you keep the bias above a critical voltage or keep increasing above it, it will stay conductive. So it is actually this volatile phenomena which enables the reprogrammable non-volatile phase change in PCM devices. So now the crystalline conductivity is nearly ohmic. It behaves like an ohmic resistor, whereas the amorphous conductivity is driven by the Poole-Frenkel mechanism, and the traditional amorphous state is high resistance, whereas after the Poole-Frenkel effect or the Ovonic threshold switching, it becomes more conductive. So let me just summarize. So in essence, two types of switching actions occur inside PCM devices. The primary or the non-volatile switching action is the phase change switching, where you're switching between amorphous and crystalline phase, which is the final low resistance or high resistance state where you want to program the device. Then there is the Ovonic threshold switching, which is change from one type of amorphous state to another type of amorphous state. So this is not the phase change for amorphous to crystalline, but this is a low conductive amorphous state to a more conductive amorphous state. So this is the volatile or the OTS switching, and this actually enables the reprogrammability of the phase change devices. If OTS effect were not there, you would have only one-time programmable PCM devices. Okay. So this is the basis of the PCM switching physics. Now, if we start with any type of PCM device from amorphous state, what you see on the y-axis is the resistance, the measured resistance of the device. On the x-axis is the applied stimuli to the device. So if we are starting, let us say we start with the device in a high resistance state, so initially, or an amorphous state, you will see that initially the resistance is high. As I keep successively applying some stimuli, the device would begin to slowly crystallize, because and the resistance starts going down slowly. So what is happening here is that I am heating the cell with these incremental programming conditions, but I am heating it above crystallization temperature. I still haven't reached the melting temperature. Now, at this point of time, I have crossed the temperature where it is the melting temperature, and thus it begins to re-amorphize, and because of this re-amorphization, I have an increase in the resistance. So your typical resistance versus voltage curve for a PCM device would always look like a U-shaped curve if you are starting from a resistance state, high resistance state. If you're starting from a low resistance state, it will look like a S-shaped curve, and it would start from here. So just by looking at this curve, you can see that there are many ways to manipulate the behavior of the device. If you change the pulse widths, if you change the pulse rise time, fall times, or the programming rise time, fall times, you can create a lot of combinations of different resistance states, meaning you have a lot of freedom for programming or manipulating the cell to multi-level or intermediate amorphous states or intermediate crystalline states, and that kind of behavior actually opens doors for realizing many different forms of computations that we want to do with these PCM cells. So when we look at in-memory computing or near-memory computing or different forms of in and near-memory computing, these kind of device manipulations become quite important. So this is another example just to illustrate what I mentioned before, that the same U-shaped curve, but the impact is different. The resistance state in which I end after a specific condition is completely different depending on what is the width of the pulse that I was applying. So, when you're trying to compute with this, let us say you have assigned a specific output to two different states, your operands or your inputs can just be correlated with two different pulse widths. So if you're looking for a desired output against the application of desired operands, you can make your system in such a way that a certain pulse width is encoded as first operand, another pulse width is encoded as a different operand, and what you get is a completely different result on the execution of that signal. So I think in the interest of time, I'll just skip through some points. This is again illustration of MLC or multi-level programming in phase change devices. And what it says is that based on the pulse engineering of the applied pulse, you can carefully tune the volume of the amorphous or the crystalline region in the cell and thus its resistance. So this the reason why I'm covering these points is that these are the techniques which later help you realize computation from the devices. Okay, so I'll come to one more point. So PCM devices also have the effect of resistance drift. What resistance drift means is that if you program your PCM device to amorphous state and leave it, there is a tendency for the resistance state to slowly increase its resistance. So this is a temporal effect which is driven by the power law, and in typical memory application this is seen as a problem, but because this has a specific time scale or it follows a specific exponential, there are very interesting ways to exploit this kind of behavior. When you're trying to solve some temporal equation or you're trying to realize some temporal computation, you can actually use this effect to your benefit. So I'll conclude the PCM properties over there, and now I'll quickly go into the computing aspect of in memory or let's say NVM based computing. So what I'd like to say is that computing with NVM has been around for a while. It's not a very new concept. And when do you say that whether computation is happening with NVM or not? It's basically when you exploit some core property or some physics of the device to realize a mathematical function or a mathematical operator. That is when computing happens. And as we know that these devices, they have both very distinct analog as well as digital switching properties. So there can be many different combinations through which you can get the math done. And again, the other thing that adds combinations to it is that whether you do it exactly on the device or you do it near the device. So when you do it precisely inside the device with a selector or few transistors, it's completely in-memory computing. When you do it with the device and some circuitry sitting just next to it, it becomes near memory computing. Okay, so now the traditional sense is that mostly the matrix multiplication or the vector matrix multiplication or matrix multiply and accumulate, recently that is the predominant thing which gets referred to as in-memory computing or near-memory computing. But I mean, the way I like to look at it is that any form of mathematical function or mathematical operation that your device or the underlying physics of the device permits you to achieve going from A to B is essentially, an in-memory or a near-memory compute. So if you take the entire gamut, then there are tons of different. There are at least 6 different types of computations or in-memory or near-memory that you can do with these devices. You can build computational synapses. You can build computational neurons. You can do the in and near sensor compute. If you club these NVM devices very close to some of your sensors, such as your pixel sensors, you can do some enhancement, some filtering with that. You can do some digital logic gate based computations. You can connect your devices with a few transistors to let them act as a NAND gate or a XOR gate, and you can do pure digital logic based computation. Then obviously the more recent or the more highlighted is the matrix multiplication and accumulation. And then there are also some for security applications. There is a whole bunch of computational tasks, such as generating some distributions or generating some entropy sources or seeds, which are required, that can also be achieved with these kind of devices and a few transistors. So I think with that, I'm just in time to conclude. If you have any questions or any points related to that. So.
Dr. Suri, there is already a question on the chat window. So the question is PCM technology in practice by any companies which are mainly in foundry? Yes.
Yeah, so that is a relevant question, and not just foundry. There have been products both on the embedded as well as storage side which have had PCM devices in them. So a lot of foundries are pursuing it. I think the question which is difficult to answer is that to whom is PCM, like who all are getting access to PCM technology? Like are foundries or companies using it just for their own, or are they offering it as a design service? That is a tougher question to answer. But if you're just asking that whether it is there, yes, it's absolutely there. It's been there for a few years, and a lot of effort is going on it's fully CMOS compatible. So, and it has been fabricated at very advanced nodes as well. So yes, it is there, and it is there in some products also.
Right. So thank you, gentlemen, and thanks to the audience for having been on this tutorial.